All right, welcome back to part 2 of our explainer on the failed water test. We're jumping right back onto the factory floor today to look at how tiny, seemingly insignificant physical oversights can literally destroy a system's electrical compliance.
Let's do a super quick recap from part 1 just to set the stage. Remember, an IP rating is a system property. That means individual component ratings, they're totally meaningless once they're actually assembled into a larger cabinet. You can't just go buy an IP65 rated access door, slap it onto a box, and magically assume the whole setup is compliant. It just doesn't work that way.
And this leads us to a really crucial distinction. There's a massive difference between what our eyes see and what the electrical current actually experiences. I mean, just because an earth cable looks firmly bolted and visually connected, that absolutely does not mean it's an electrically sound path. A single loose bolt, maybe a microscopic layer of oxidation, or even just some hidden paint, that can completely ruin the connection and act as a massive roadblock to safe fault currents.
So this visual deception can trigger a rapid chain reaction of failure out in the field. It usually starts with something really small, right? Something seemingly cosmetic, like a faded or mislabeled terminal block. But if those markings don't perfectly match up with the wiring documentation, a tech might accidentally swap 2 wires, and bam, that simple little mistake can result in a catastrophic reversed phase rotation downstream, or worse, an entirely incorrect vector group connection that causes massive circulating currents the absolute second you close that breaker.
Now, this weakest link principle applies directly to the physical seal of the equipment too. Like we said, a cabinet's IP rating isn't some isolated component stat. It is strictly a holistic, system-wide property. By definition, the integrity of your cabinet is defined solely by its smallest, weakest failure point. Literally, every single cable gland, rubber gasket, and door latch has to perform flawlessly together.
To put that into perspective, think of a premium IP65 rated cabinet, exactly like a waterproof raincoat. The manufacturer can certify all day that the fabric itself is 100% waterproof. But if you walk out into a pouring storm and leave just one seam unzipped, well, the water's getting in anyway. The protective rating of the fabric becomes completely irrelevant the exact moment the overall system gets compromised.
And we see this in the real world all the time. During one site commissioning, an entire, highly engineered electrical cabinet failed its IP54 water ingress check, and the engineers didn't find some massive structural flaw. Nope, they found that a single cable gland had been fitted with the wrong size rubber grommet, which left a tiny gap of just 2 millimeters. That's it, 2 millimeters. Everything else on this huge cabinet was perfectly sealed, but that one tiny gap dropped the effective protection way below spec and failed the whole unit.
Okay, let's test this weakest link concept with a quick interactive check. Imagine you're the engineer on site. You're verifying safety parameters, and your earth continuity test reads 5 ohms. But the site standard explicitly requires the earth connection to be below 0.1 ohms. You look at the cable, and honestly, it looks perfectly bolted and secure. So, is that 5 ohm reading acceptable to energize?
No way. It is absolutely not acceptable. A 5 ohm reading is a massive red flag. Remember our rule about visual versus electrical connections? A bad earth path with 5 ohms of resistance means that during an internal short circuit, that massive fault current cannot return cleanly to earth. Instead, lethal touch voltages could develop right on the physical metal frame of the equipment. So if an operator touches that panel, the current goes right through them. You absolutely have to stop and investigate that high resistance before you ever even think about applying power.
By wrapping your head around these physical realities, you can now confidently tackle a visual and physical compliance check. You know exactly why you need to look out for faded labels, mismatched grommets, and hidden resistance. But this leaves us with a pretty provocative question for our next explainer. Your equipment might look physically safe right now, but what happens when you actually introduce real voltage and current? I mean, will it survive a real lightning strike? Next time, we're going to dive into the 13 crucial winding and phase verification tests that actually prove a transformer performs exactly as designed. See you then.